In this lesson, we see how the entries from the confusion matrix are used to gauge the performance of the logistic regression model. In our example, we will assess the performance of the fitted training data. So, there are some terms that you may have seen previously, but I want to make sure that we understand how they are defined. So, sensitivity, specificity, and false positive rate. So, sensitivity is also called the true positive rate and is defined as follows. It is the true positives over true positive plus false negative. Specificity is what is called the true negative rate. It is true negative over true negative plus false positive, and false positive rate is 1 minus specificity, and it is equal to false positive over true negative plus false positive. We use sensitivity and false positive rate in ROC curves later on. There are a couple more metrics that you may encounter: precision and accuracy. So, precision is what is the probability that you have y equals 1 given the predicted value of y is equal to 1. So, it is true positive over true positive plus false positive, and accuracy is defined as true positive plus true negative over the entire denominator that you have here. So, these are the metrics that you may encounter with logit models and other prediction models. Some other terms that you may encounter are type 1 and type 2 errors that you may have encountered in your introductory statistics classes. We will see they are also used out here with logit models. So, false positives are also called type 1 errors, that is, you are falsely rejecting the true null hypothesis. Remember that a false positive occurs when the true value of y equals 0, but the predicted value is 1, and increasing the cutoff decreases type 1 error. False negatives are also what is called type 2 errors. You have incorrectly retained a false null hypothesis. Remember that a false negative occurs when the true value of y equals 1, but the predicted value is 0. Increasing the cutoff increases type 2 error. So, type 1 and type 2 errors occur in business applications also, and the cost of making a type 1 or a type 2 error depends on the business application for which you are making predictions. Assume you have a marketing application and y equals 1 means customers who will purchase. Say you classify a non-purchaser, let us say using a logit model, as a purchaser. So, a non-purchaser has y equals 0. If you classify him or her as a purchaser, you are predicting y hat equals 1. So, that is a false positive. In this particular scenario, you will typically have moderate loss for false positives or type 1 errors, because you are probably spending a little bit of advertising dollars or marketing costs to advertise to a bunch of people who probably would not purchase your product. In another example in business, you have a banking application, and in this case, let us say y equals 1 means customers who default on a mortgage. Say you classify a customer who will default y equals 1 as a non-defaulter. So, it is a false negative. This false negative or type 2 error could be costly to the bank, since that customer's loan or mortgage may have to be written off. So, we are going to use the confusion matrix to calculate sensitivity and specificity, and we have seen these values from the crosstabs function in R, which got us these values: true positives, false negatives, true negatives, and false positives, and we can calculate sensitivity and specificity for model 4. So, sensitivity is true positive over true positive plus false negative. It is 105 over 333 or 0.32. Specificity is true negative over true negative plus false positive, and it works out to 9627 over 9667 or 0.996. So, this is at a cutoff value of p equals 0.5. I could increase the cutoff value of p to 0.9 and do the calculations are, do the crosstabs, do the predictions and so on, and here is what I get. I get this set of entries for the confusion matrix, and then the sensitivity here is 10 over 333 or 0.03. That has reduced dramatically, and the specificity has increased to 0.9998. So, increasing the cutoff value of P, if we increase this cutoff, true negatives will increase and false positives will decrease. If we increase the cutoff, true false negatives will increase and true positives will decrease. So, by these definitions of sensitivity and specificity, as we increase the cutoff in this model 4 from 0.5 to 0.9, sensitivity decreased from 0.32 to 0.03, but specificity increased from 0.996 to 0.9998. So, this is how the I've used R and the code that I used to plot the prediction and the ROC curves and finding the area under the curve for a logit model. To do that, I have installed and used two packages in R, ggextra and ROCR. And this is the ROC curve or receiver operating characteristic curve for our logit model 4. The x axis is the false positive rate or 1 minus specificity. The y axis is the true positive rate, which is the same as sensitivity. So, the ROC curve is used to show the diagnostic ability of a binary classifier. So, in this case, we want to have a curve which is looks like this particular curve, where the curve tends towards the top left. So, the area under the curve, if you measure it, we get a value in this case of 0.95, and we want this value to be greater than 0.5. So, in this particular case, this particular model seems to be doing quite well as far as the ROC curve is concerned. Before we end this lesson, I have a couple of quizzes. Please take a moment to answer this quiz. So, given this confusion matrix, true or false, sensitivity is 105 over 333. Answer is true. It follows the definition. It is true positive over true positive plus false negative. It is 105 over 333. The second question in this quiz is specificity 40 over 9667. False, because specificity is true negative over true negative plus false positive. So, it should be 9627 over 9667. So, in this lesson, we saw how the entries from the confusion matrix are used to gauge the performance of the logistic regression model. In our examples, we assessed the performance of the fitted training data. You could have also used a fitted model on a training data set and developed a separate confusion matrix on the test data. So, this is a recap of what we have done in this module. We looked at odds and how they are defined. We looked at situations where you have dependent binary variables for in business problems. Then we defined the logistic function and seen how it is used in logistic regression. And then we used the logistic function, applied it in the default data set to create 4 different models. The first one did not have a predictor variable. The second one had a single 0-1 predictor variable. The third model had a single continuous predictor variable, and the fourth model had multiple predictor variables. We had the confusion matrix and saw how logit models can be used for making predictions, and then finally we looked at other metrics like sensitivity, specificity, and then the receiver operating characteristic curve, ROC curves, to gauge the performance of the logistic regression model. Thank you.